there are two types of broadly speaking, okay, there are two types of machine learning problems. One is the problem that you have seen so far, which is called regression problems. And the second type of problems are called classification problems. Now, the difference between them is that in regression problems, you are trying to predict a value. So for example, you are trying to predict like whether the band gap of a material is 1.5 electron volt, or is it 1.49 electron volt, or 1.0 electron volt, right? A classification problem is very different. A classification problem, you are only trying to predict categories, right? So in other words, your data is not in the form of a continuous value, but rather in the form of a class. So for example, you may want to predict whether something is a metal or insulator. So those are just two classes, right? So you may want to predict whether something is a superconductor or a non-superconductor. Again, that is a classification, right? So linear methods can also be used for classification as well, okay? Now, when we do use linear methods for classification, what it simply means is that your decision boundaries are linear. In other words, you have, if you think of it in a two-dimensional space, you just have a line that is separating between the data that will fall into one class and the data that will fall into another class, okay? Now, despite seemingly that this is a very simple form of machine learning, it actually is surprisingly effective across a large spectrum of data sets, okay? Even when you compare this to other more sophisticated machine learning models that we are going to talk about going forward, okay? So how do we actually go about using linear methods for classification? Now, to demonstrate these methods, we will first discuss this toy dataset that I have generated. So this toy dataset comprises of 2,000 binary compounds. Binary compounds meaning that they are formed from two elements only. And these 2,000 binary compounds have experimental band gaps that have been measured. Now, experimental band gaps, you know that, for example, metals are materials with band gap of 0, while insulators are materials with band gap not equals to 0, right? Now, obviously, we can define subcategories if you want to. For example, we may want to say if the band gap falls between 0 to, say, 1 eV, those are semiconductors. Now, for the purposes of this exercise, we are not going to bother with that. We are going to just define the very simple classification. If something conducts electricity, it has a band gap of 0, it is a metal, right? And anything else, we are just going to consider it as an insulator. Now, using PyMatGen, which is our materials analysis code, we can actually generate a lot of simple features, and this is what you're going to be doing for your lab number 2. Here, I'm actually going to just use 2 features, and these 2 features sounds very simple, right? One feature is the mean of the electronegativity between the elements A and B for that binary alloy or binary compound, sorry. And the other one is the absolute difference between in electronegativity between elements A and B. Okay. Now I have this question: why did I actually choose these 2 as my features? Anyone wants to hazard a guess? Why would I think that electronegativity has anything to do with whether something is a metal or insulator? Yep. Okay, great. So, excellent answer. So, one of the things we know about the periodic table is that most of your metals are on the left side of your periodic table, right? And they have small electronegativities, small to intermediate, right? And all your anions, which are your things like oxygen, your sulfur, your fluorine, and that sort of thing, they all sit in the top right corner of your periodic table, which have very, very high electronegativities. So when you actually have two compounds with very different electronegativity come together, they tend to form ionic compounds, right? This is your high school chemistry, right? So things like lithium fluoride, lithium oxide, sodium chloride, all these are very highly ionic compounds. They are formed when two very electronegative, two elements with very different electronegativities come together, because then one compound will tend to give up its electron to the other compound, to the other element, and then you form an ionic compound, right? Now, in contrast, metals tend to be formed between elements with very similar electronegativity, right? So when two metals come together, like say iron and manganese, they tend to form alloys, which are or copper and gold, they tend to form alloys, and alloys tend to be metals, right? And this is the reason why I just chose to use these two features as the potential features for my classification, right? Now, one of the most useful ways you can visualize the data is to just plot the data as a function of your features, right? And because I only have two features, it's actually quite easy. So what I'm going to plot is I'm going to plot my difference in electronegativity between the elements on one axis and the mean electronegativity on the other axis. And I'm going to color my dots based on whether they are metal or insulator, right? And immediately from the plot, you can see that there is some clear relationship, right? Because all my insulators tend to be on this top right corner, and all my metals tend to be on this bottom left corner, right? So quite clearly, I think my choice of features seems to be in line with my intuition, right? Now, obviously, you shouldn't go too far with this kind of analysis. You shouldn't over constrain yourself in terms of the features that you select, but sometimes your domain knowledge can actually help you think of what would be the most sensible features to use, okay? Now, to generate the features, I actually have code that shows you examples of how you will go about creating those features, right? So, first of all, we are going to use pandas to read in the binary bandgap data set, and to basically calculate the electronegativity differences and the mean. What we first need to do is that we need to pass all the formulas into composition objects. A composition is just a Python representation of the formula of your compound. So like, for example, Fe2O3, right? Now, in PyMagen, the composition essentially is a dictionary-like object. It comprises of elements to amounts keys, okay? It's basically elements. It is something like, for example, if you have Fe2O3, it's basically a dictionary that has this form, okay? And what you notice is that basically the keys comprises of all the elements in your formula, and the values are essentially the amounts of those elements, okay? And that is basically what is a composition. And what I first do is that using PyMagen, the composition object, I'm going to pass all my formulas. All you need to do is to just give the string formula to the composition object. It will automatically pass the formula. And then the electronegativity of each element is in the attribute X. So I'm going to create a string of the elements, the electronegativity of all the elements for each line. And then I can calculate the mean by taking using the NumPy function mean, or I can take the difference by taking the max of the electronegativity minus the minimum of the electronegativity, and that gives me my difference, okay? And also the data is actually the raw bandgap. So what I'm going to do is that I'm going to create my target, which is the class, whether it is insulator or metal, by defining that if the bandgap is actually less than some very small number, like 1 e to the power minus 5, I'm going to classify it as in class 0, which is basically metal, and otherwise I'm going to classify it as 1, okay? So let me go to my example. over here. And oops. So if you look at this code, if you read in the file itself, this is basically what is the raw data of the file. It is just basically a string formula together with a bandgap value, okay? So this is the raw data that I actually got from a previous work by someone who actually compiled all that data, okay? And then here I basically pass all the formulas into actual composition objects. So pandas data frames, you are not limited by the kind of objects that can be contained in your data frame, okay? It doesn't just have to be numbers or strings, right? It can actually be any type of Python object. And in this case, I'm actually creating a column with the corresponding composition object. Now, this doesn't really tell you what the formula is because this is not the full representation of the formula. But trust me when I say that this is actually a PyMatGen composition object, okay? Now, I then go through the code that I just showed you. Essentially, I generate the mean electronegativity and the difference in electronegativity, and I generate the class. Now, eventually, what I have is a pandas data frame that looks like this, okay? Now, these two will basically be my features, and the class will be my target, all right? So in this case, remember, we are trying to do a classification problem. We are not going to use the bandgap itself as my target. I'm going to use the class itself as my target, okay? Now, so essentially what I'm asking is, can we actually predict the class from these two features, right? Some function of mean electronegativity and difference in electronegativity, right? And let's think about the ways in which we can do this, right? Now, the most naive way in which we can do this is we can basically just create a M by K indicator response matrix, which basically says that if I'm in class K, then I have a 1 in this in the K column. If I'm in class 1, I will have a 1 in my first column. And basically, this is an encoding of each of the classes for every single observation, okay? So you can imagine for the metal insulator data set, what you will have is, for example, if the first compound is actually metal, you will have something like that looks like this. If the second compound is an insulator, you will look something like this. And you basically have every single row is either 1, 0 or 0, 1, depending on what class it belongs to, right? Now, for each of the response variable, I will treat it as essentially like a regression problem. I'm going to assume that this K response variable is a linear function of my observations of X, okay? So this is just my standard linear regression equation, okay? So I'm assuming f of K of X, which is based on each individual column, is equals to some intercept plus this series of coefficients multiplied by my feature vector, right? Now, how do I then decide after I have already fitted all my coefficients whether something belongs to class 1 or class 2 or class 3 or class K, right? It is actually very simple, right? All that I need to do is that I'm going to calculate f of K of X for every single data point based on the feature number, okay, for every class. And then I take the highest value, right? So, and the highest value basically says that if I'm predicting 0.1, 0.2, 0.1, I'm going to assume that 0.2 is basically my correct class, okay? So the decision boundary between each of the classes would then basically be given by the line in which your f of K of X and f of L of X is actually equal, okay? And in this way, your input space is then divided into regions, okay? So obviously, there's no restriction that says that I must only use a linear function of x, right? I can always augment that relationship by using polynomial transform, basis functions, whatever that I choose to do, which was what we actually covered in our linear regression um, section. Okay. Now, so basically, the answer, one of the most naive way in which you can actually go about doing this is to essentially just do linear regression of your indicator matrix. You treat each column of y as a target. You do a least square solution. This is analytical. Remember, we don't actually need to do any numerical optimization to find the solution. This is actually an analytical solution. Your predicted y is then given by this expression over here, right? And for each new observation, what we then do is that we are going to compute every single one of my f of k of x, and then the largest component will result in classification k. Okay? Now, this is actually a very simple way of doing linear classification. That unfortunately there are very big issues with doing it this way, right? And one of the issues is that you can actually have masking of classes when your number of classes is actually greater or equals to 3. So in other words, other than your binary classifications, you can actually have situations which arise where your predictions only predicts everything to be in 2 classes, even though when in reality there is more than 2 classes. Okay, so this is an example, right? So this is an artificial data set, of course. This is not a data set that is based on some generation. So this is obviously a data set that comprises of 3 Gaussian functions of x1 and x2. There's one distribution, one cluster over here. There's another cluster over here, and there's another cluster over here. Now, despite us treating it as a 3-category problem, what you will find is that when you actually do the linear regression for this problem, your decision boundary is actually over here, okay? And this decision boundary is going to put anything that falls on this side of the line as category 1, and everything that is on this side of the line as category 3, and nothing is going to ever be classified as category 2, okay? So this is what is called masking of your categories, okay? So this is obviously a severe limitation, right? So especially if you're not working with your simple binary classification problems, right? So how do we actually go about addressing this issue, right? To address the issue, we actually use what is called discriminant analysis, okay? And this is actually a very powerful technique, okay? So if you are actually facing with a classification problem, I will actually encourage you that by default, you should first try your discriminant analysis, okay? First try your linear discriminant, quadratic discriminant analysis before you go and try some sophisticated thing like, oh, I'm going to try to throw a neural network at the problem, okay? So more often than not, the discriminant analysis may actually suffice for the problem that you're interested in, okay? Now, discriminant analysis is based on Bayes' rule. So again, this is why a prerequisite for this course is that you must have taken probability and statistics before. Okay, you need to know what Bayes' rule is, right? So from Bayes' rule, we know that the posterior probability that something is in class K given your observation X is equals to the product of your distribution of X multiplied by the prior probability of being in class K divided by the summations of all that of that product for every single class. Okay, so now the f of k of x are what are called class conditional probabilities. Okay, so in other words, what is the probability distribution of x given that something is in class K, right? Yeah. So it is basically given is the probability of x being the value x given that G is actually in class K. And the pi of K is basically what is the prior probabilities of being in class K. In other words, in your data set, do you have a very skewed data set in which you have 10% of data being in class 1 and 90% of data being in class 2? or do you have a more even split, 50-50 between class 1 and class 2, right? Now, of course, this gives us a new problem, right? We actually need to know what our class conditional probabilities are. And we often do not have that information, right? We don't actually know what the class conditional probabilities should be. Now, whenever we don't know anything about the data set, one of the most common ways we deal with this problem is we just throw a Gaussian distribution at it, right? Because we know that very often with instrument noise and all kinds of other kinds of noise, a Gaussian distribution is a somewhat reasonable approximation, right, for distribution, right? So we assume Gaussian class densities, which means that now each of my f of k of x is given by this Gaussian function over here, all right? So this is obviously an n-dimensional Gaussian function. So what you have is x minus the mean of k. This is your Hessian matrix, and this is basically just a prefactor, okay? So you assume that each of the f of k of x actually takes this form. All you need to basically determine is basically what is the mean of your, the k, class k, and also this covariance matrix over here, okay? So in linear discriminant analysis, what you actually assume is that all your covariance matrices are going to be exactly equal, okay? They actually have, all the classes have the same covariance matrix, so you are not going to use different covariance matrices for each of your classes. And to compare two classes K and L, we can basically compare the log ratios, okay? So if you want to know whether between class K and class L, which one of them is more probable, we take the ratio between them and we take the log, okay? So obviously, if this is bigger than this, then you have a log of a number greater than 1, so it's greater than 0. If you have, if it is more probable that you're in class L, then this is less than 1, and then you have a log that is less than 0, okay? So this then gives you a very simple way of figuring out a yes-no answer to whether it is more probable being in class K or class L, right? Now, you plug in your formulas for your posterior probabilities. In other words, just this function over here, you plug it in. The denominator is the same, they cancel out. So basically all you have is just your f of k of x and your pi k, okay? And you split up the logs, and then you basically have this function over here, right? So at the decision boundary, essentially what's the boundary in which you are indifferent whether something is in class K or class L. Essentially, that's when this log is exactly equals to 0, in which your posterior probability of being in class K and your posterior probability of being in class L is exactly equal, right? And if this is 0, essentially what you see is that this is actually a linear function of your x, okay? So this is why this is called linear discriminant analysis, right? So to determine which is the predicted class, all you need to do is basically you compute this for all your different classes given your observations, and you then take the value of k, the class k that actually has the highest value for your this function, okay? And that gives you your prediction for your class k. All right. Now, obviously, we do not know the prior distributions and the covariance matrix. So in order for us to do those computations, we need to estimate those values. And from your statistics class, you should have already known that, well, the easiest way for me to estimate the prior probability is to basically just take the number of data points that I actually have being in class K divided by the total number of data points. That basically tells me what's the probability of something being in class K without actually doing any analysis, okay? The means are, of course, easy. We take everything that is in class K. We then take the mean of that data. That basically gives me the each of the means of the classes. And then for the covariance matrix, we actually can estimate it from this expression over here, which is something that is just an extension of the variance estimate that you actually learn in your statistics course. Okay, so this is just think of this like a multi-dimensional variance estimate for your data set. Okay, so the nice thing about this linear discriminant analysis is that you don't actually run into the same problem that you have masking problem. So if you actually have 3 or more classes, you actually don't have that problem. Okay, so let's look at how does this linear discriminant analysis work for the data set that we have. So this is actually what happens. So you see that in linear discriminant analysis, because my covariance matrices are all the same, you will notice that the ellipses that are generated. So this is essentially this is an indication of the distribution of the means and the variances of your data. You will notice that the ellipses are all oriented in the same direction and they have the same size. Okay, so this is the mean of being in class 0, and this is the mean of being in class 1, and the decision boundary is given by the white line over here. Okay, so and this is basically the result of fitting a linear discriminant analysis to this data. Okay. All right, so let me go back to the example just to show you how you go about doing this. Now, I want to reiterate that the best practice is that you cannot actually fit your model to the entire data set. Remember? Okay. So again, I need to reiterate this again and again. Don't ever fit your data to the entire data set and just calculate the training error and then say, oh, okay, this is my R square is equals to X. Okay. That is not an accurate reflection of how good your model is. Now, for the purposes of our classification problems, I'm going to not do K4 cross-validation. You can do K4 cross-validation, of course, but I just want to make it simple. What I'm going to do is that I'm going to split my data into a training set and test set. Okay. So in this case, I'm going to use a train test split of 0.1. What this means is that my test set is going to be 10% of the data that I have. So out of the 2,000 compositions that I have, I'm going to choose 200 of them to be my test set, and the other 1,800 is going to be my training set. Okay. So using the scikit-learn function train test split, you automatically they can actually automatically generate your feature sets and your training and test sets for your targets and as well as your features automatically. So just a reminder that we are only using 2 columns to be our features. Okay, so that's why I have this. My feature is basically just my mean electronegativity as well as my difference in electronegativity, and my target is my class. Okay, my target is not the actual band gap, right? So to do my linear discriminant analysis in scikit-learn, there's actually a package called, very helpfully, discriminant analysis, and there's linear discriminant analysis in this package, and all you need to do is you do exactly as what you have done previously, which is basically you call the fit function. So I'm going to just scroll all the way down. You initialize your linear discriminant analysis. The solver, you can actually choose different types of solver, but usually the default is fine. Here I use the SVD solver, and then you just call fit on the training data, and to predict the data, you apply it on the test data. Okay, this method that I wrote here is basically just a way of plotting this nice little plot that I have here. I'm not going to go through the details of the plotting, okay? So you can read this up yourself. But by and large, even with this very simple example, I really can achieve a close to 80% accuracy in classifying whether something is a metal or insulator, okay? So, this is the result, okay? And you notice that this plot has relatively few data points. compared to the this plot. The main reason is just is 10% of the data points. Okay, so this is the test data only, right? I didn't plot the training data. Okay, any questions regarding the LDA? No? Okay, so now, of course, we can extend our linear discriminant analysis beyond just linear discriminant analysis. We can do quadratic discriminant analysis. And in this case, your decision boundaries are no longer linear, but rather they are quadratic, right? Now, the main difference between quadratic discriminant analysis and linear discriminant analysis is that you no longer assume that your covariance matrix is identical for all classes, okay? So remember, one of the main assumptions we made for our linear discriminant analysis is that no matter what class we have exactly the same covariance matrix. Now, sometimes this is a reasonable assumption, especially if you assume that the covariance is the result of some instrument noise, which is consistent regardless of what the magnitude of your value measurement is. But more often than not, that's actually not a good assumption, right? So what you then do is that instead of doing this, you now actually have to estimate each of the covariance matrix for every single category by itself. Okay. Now the formula is still the same. Okay, you are still estimating the covariance matrix using the same formula. It's just that instead of assuming they have the same covariance matrix and you use the entire data set, you're going to estimate covariance matrix for class 1, covariance matrix for class 2, covariance matrix for class 3, all the way for under class K. Okay. Now, with a non-equal covariance matrix, then you no longer have cancellation of terms. Then you actually do need to, but the principle of the application is still the same. Essentially, what you do is that after your fitting, you then calculate this for your feature vector X, and then you take the argument, the class K that actually gives you the highest value for the predicted value of this expression over here, right? Now, for the meta insulator example, if you actually do quadratic discriminant analysis, this is basically what you get. So the decision boundary is over here. Okay, so you notice that now the decision boundary is no longer just a line, right? It's actually this curve over here. So that's one feature. Okay, the second interesting feature for your quadratic discriminant analysis is that now your ellipses are no longer the same, right? We are no longer assuming that they have the same covariance matrix. So each of the classes have their own estimated covariance matrix. And this is the covariance matrix of being class 0. And this is the covariance matrix of the class 1 data. Okay? So, and it does seem that if you look at this, the ellipse of my insulator data set is bigger, right? It actually has a much larger ellipse compared to my metal data set. And it's kind of expected, right? Because my metals tend to be clustered in one specific region of my periodic table, okay? All right. Although this is different, quadratic discriminant analysis is, of course, different in terms of slightly different in terms of formalism. The way that in which you apply it is still the same. So this is the nice thing about scikit-learn. You actually only need to learn the formalism once. And once you learn that formalism, you just cut and paste and it is all the same code, right? You just change this from linear discriminant analysis to quadratic discriminant analysis. And you just call fit and predict and you're done, okay? All right. Just to show you, this is basically, again, the plotting. Now, I want to show you that it doesn't mean that just because you are choosing quadratic versus a linear discriminant analysis, your performance is necessarily better. In this case, it's actually a case where the performance is actually slightly worse, okay? So here the accuracy of predicting whether something is in a metal insulator, the accuracy has dropped to 0.778. Previously with linear discriminant analysis, I got something at 0.78. Of course, this difference is very small, so maybe it may mean something, it may not. Maybe with a different split of data, it may give you different results, okay? But this is just to caution you that it's not always that the most sophisticated model is the best, right? Now, what you notice is that I also plotted the actual class of the test data. The blue dots are basically my metals, and the beige dots are basically my insulators. And you will notice that there are, of course, misclassifications as well. So for example, everything around here should be considered an insulator, right? But there are obviously metals with band gap 0 even on the wrong side of the border, okay? So, and vice versa, right? There are also insulators which we wrongly classify as metals, all right? So this is not surprising. Okay, any questions regarding discriminant analysis before I move on? No? Okay, good. You in your lab number 2, you will be asked to do discriminant analysis on your data sets as well. So the data set will be slightly different, but by and large, the code examples is still the same. Just you can use the example that I showed in the lecture and then apply them to the data set that you have. Okay. Now, another way of doing classification with linear models is through what is called logistic regression. Now, I know that it says regression there, but it actually is a classification technique. Logistic regression is not a regression technique, okay? Now, the way that you do logistic regression is that you are going to assume that the posterior probabilities themselves are some linear function of your feature vector. So in this case, the log of the ratio between your classes is given by this linear function of x. So beta 1, 0 plus beta 1 transpose x, okay? And so on and so forth. You can express it in terms of the ratios of 1 to k, 2 to k, and k minus 1 to k. And if you rearrange the terms, you can actually show that the posterior probabilities are then given by this expression over here, okay? So essentially, it is an exponent of this function divided by 1 plus the summation of the exponents of all the other, of all the different classes, okay? What does this remind you of? Anyone? What does this logistic regression expression remind you of? Anyone has done thermo? No thermo class in nano engineering? That's somewhat surprising, okay. This is basically, this looks a lot like your partition function, right? For the statistical mechanics. Essentially, the probability of being in some class or some state is equals to the exponent of some energy function of that state divided by the sum of all your exponents, which is your partition function. Okay, so since you haven't done thermo, that's fine. But essentially, this is what it is. Okay, so basically, when we try to solve the coefficients, so essentially, in order for us to do logistic regressions, what we need to solve for is basically all these coefficients, beta 1 naught, beta 1, beta 2 naught, beta 2, so on and so forth, okay? To solve for all these coefficients, we basically use what is called a maximum likelihood technique, okay? So we define the likelihood of the coefficients beta as being the sum of all the log of g of k, given that x equals to xi, okay? So in other words, I'm going to look at the, given the data set, I'm going to look at the posterior probabilities, and I'm going to define the likelihood as this, and I'm going to solve for the coefficients that maximizes this likelihood function, right? So the way that I would need to find the coefficients that maximizes its value, essentially I do differentiation. So I differentiate my likelihood function with respect to beta. I set it equals to 0, and then that gives me all my beta values. Okay, and this leads to equations that are non-linear in beta, and usually to solve that equation, you use some optimization technique. So, for example, your BFG, your Newton-Raphson algorithms or your BFGS algorithms. There are many different types of optimization algorithms that are here that can be used. But basically, what you're trying to do is to solve for the beta. Okay. Now, just to show you how it works on our very simple data set. Again, so for logistic regressions, it's under the linear model package in scikit-learn. Still very similar to what you have done before. You basically import the logistic regression class, and then you feed it to your data, and then you predict it on your data. And this basically gives you this decision boundary over here. The accuracy is basically similar to your linear discriminant analysis. Okay, so this is actually a very simple data set. So there is no, and with very simple features, there are only 2 features. So there isn't really that much of a difference in performance between all the different models. Okay, so but for your lab 2, I would expect that there will be actually more differences between different models. Okay, because for lab number 2, you are not going to just use 2 features, but rather you're going to use a set of like 6, 7 features, right? All right, that concludes this lecture on linear methods for classification. Any questions?